Okay, good evening. So Ashish, Varun, Rishi, Vasant or Charitre? What about others? Is it okay? Okay, Praharsh. Okay, Yash. Okay, so good evening all. Now, today we will do next part, that is relative reactivity of aldehydes and ketones. Relative reactivity of aldehydes and ketones. Okay, Sahil आ गए? Wait. Okay, good evening, Kashmira. Yes, so relative reactivity of aldehydes and ketones. So in aldehyde we have C double bond O H and there is R or H, right? In ketone there is R or AR. Here H, R or AR, anyone. But here there are only alkyl or aryl groups in ketone. But in aldehyde, one position is occupied by hydrogen. Okay? So now the factors reactivity. First factor is steric. So tell me, on the basis of steric factor, out of aldehyde and ketone, which one, in which case carbon is more hindered? Steric means hindrance due to size of the groups attached. So tell me, out of aldehyde and ketone, carbonyl carbon is more hindered in which case? In which case carbonyl carbon is more hindered? Yes. Fast. Very good. In ketone, because in ketone there are bulky groups. These are the bulkier groups. In this case, one group may be bulkier, but other group is very small. So, steric hindrance is more on carbonyl carbon in case of ketone than that of aldehyde, right? So more is the steric hindrance, lesser is the ability of nucleophile to attack on carbonyl carbon. Okay, that means according to steric factor, ketones are less reactive than aldehydes, because carbonyl carbon is more hindered, more sterically crowded as compared to aldehydic carbonyl carbon. Got it? So this carbonyl carbon can be easily approached by nucleophile. Nucleophile can easily approach this carbonyl carbon, being less sterically hindered, but carbonyl carbon of ketone is more hindered, therefore nucleophile will feel more hindrance to attack at this carbon. Done? Any doubt in the steric factor? Or anyone who has doubt what is steric? Steric factor means hindrance due to size. That means as size of the alkyl group or aryl group increases, steric hindrance increases, and so reactivity decreases. Got it? Means I can write here, as size of groups attached to carbonyl carbon increases. Okay, so I can write here, steric hindrance increases, so reactivity decreases. Okay? Right. Second factor is electronic factor. So as per the electronic factor, electronic factor means inductive and resonance effect. So you know, as electron releasing power of groups attached to carbonyl carbon increases as electron releasing power of groups attached to carbonyl carbon increases, electron density on carbonyl carbon increases. So attack of nucleophile on carbonyl carbon. Just tell me, if electron releasing effect is more, so tell me, nucleophile will easily attack or it is attacked with difficulty? Yes, tell me. Okay, Subhashri, good evening. Okay, you are welcome first day. What is your name? Very good. It is more difficult. What about others? Why are not replying? Only Sahil. Okay. So, attack of nucleophile on carbonyl carbon is bit difficult. So, reactivity of carbonyl compound decreases. Reactivity decreases, right? And reverse for electron withdrawing groups. So if electron releasing groups increases, reactivity decreases. So let us study for aldehydes first. So tell me, if we have formaldehyde and acetaldehyde or propionaldehyde, what is the order of reactivity? What is the order of reactivity? Let us take it as first, second and third. So what is the order of reactivity? Very good. First is greater than, very good Ashish, Sahil. Because as we go on right side, first of all, you know, size of the group increases. So because H remains same, but here H, CH3, CH2 CH3. Steric hindrance, size of the group attached increases, means steric hindrance increases. At the same time, plus I effect increases. Plus I means electron releasing effect, and that's why reactivity decreases. So formaldehyde is more reactive than acetaldehyde, which is more reactive than propionaldehyde. Done? Good. Very good. Because you know, plus I effect of CH3 CH2 is greater than CH3 greater than H, and same is the hindrance. Okay, now this is all about aliphatic aldehydes. As number of carbon atoms increases in the alkyl group, hindrance increases, plus I effect increases, and so reactivity decreases. Right? Now tell me, if we have benzaldehyde and acetaldehyde or any alkyl group, so what is the order of reactivity? Actually, electronic effect is more than steric. Okay, we will say both effects, but electronic effect has upper edge. Okay, very good question, Sai. Now tell me, out of benzaldehyde and acetaldehyde, or we can say aromatic aldehyde and aliphatic aldehyde, what is the order of reactivity? Which one is more reactive? Yes, fast. Out of means aromatic aldehyde and aliphatic aldehyde. Which one is more reactive? Very good. Vasant, why? Why is it so? Yes, fast. Steric hindrance. But before that, let us look at the electronic factor. Steric factor is also one of the thing, but first of all we see electronic factor. So say if phenyl has minus I effect, phenyl has minus I effect, so as phenyl has minus I effect. So its reactivity should be high, should be more than this. Methyl has more electron releasing effect than phenyl as per inductive effect. I am talking in terms of inductive effect only, right? But for here main effect is conjugation effect. Main effect is conjugation effect. So we will write as CO group has minus M effect, or you can write minus R, okay? Minus M effect. So electron density on carbonyl carbon is more. Electron density on carbon carbon is more because of minus M effect of CO. Because if it has minus M effect, ring has plus. That is called mesomeric. Okay, just like resonance. It is resonance means this is called conjugation effect. Okay, because of this conjugation effect of CO, electron density of the carbon carbon is more. So attack of nucleophile is difficult. So aromatic aldehydes are less reactive than that of aliphatic aldehydes, or you can say its resonating structures. See, this is benzaldehyde, right? So C and O, when this carbon releases electron towards oxygen, at the same time pi bond from the ring goes here. So above all, there is no positive charge on carbonyl carbon. Okay, so in this way it gets negative charge and positive charge is on the ring. So it becomes see in none of the resonating structure there is a positive charge on the carbonyl carbon. Okay, so resonance hybrid is right. It is like this. So in none of the structures there is a positive charge on the carbonyl carbon. So attack of nucleophile is difficult on the carbonyl carbon containing phenyl group. That's why aromatic aldehydes are less reactive than aliphatic aldehydes. Okay, because in aliphatic aldehydes, you can say, if we draw the structure, it is always like this. There is only plus I effect of alkyl group, but here because of minus M effect of CO, or we can say plus M effect of phenyl ring, there is no positive charge on carbonyl carbon. Okay, so that's why aromatic aldehydes are always less reactive than aliphatic aldehydes towards nucleophilic addition reaction. Okay, and if we compare aldehydes and ketones, so there is clear cut difference that aldehydes are always more reactive than ketones, aromatic as well as aliphatic. See, if we have this, or we can write like this. Look. Okay, this is aliphatic aldehyde, that is aldehyde, and this is ketone. So in ketone there are bulkier groups. On both the groups are bulkier. On the carbon-carbon, here only one side is the bulkier group is attached. On the other side there is small hydrogen. So from this side attack can take place easily. Okay, so aldehydes are always more reactive than ketones, because ketone has both steric hindrance, more steric hindrance, as well as more electron releasing groups. So less reactive than aldehydes. Right? Okay. So see, this one is more reactive. Aliphatic is more reactive than aromatic. It is more reactive than aliphatic ketones, more reactive than this, which in turn more reactive than this. Okay, it is. Can I write here? Okay, sorry. Difficult to write here, but I am simply writing it like if we have H and H. Okay? Yes, tell me. Up to this, any doubt? Yes. Okay. So let's proceed to the next part. Okay, so nucleophilic addition reaction. Nucleophilic addition reaction. So if we have this aldehyde, reaction takes place with HCN. So you know, in HCN there is H plus and CN negative. So, and C and O is negative, C is positive. So OH CN. Such a compound is called cyanohydrin. But this HCN is very weak acid. HCN is a very weak acid. That's why HCN is preferably taken with sodium hydroxide, means in the presence of base. So in the presence of base, what would happen? We can get CN negative. Okay, and a positive CN negative along with H2. Okay, if we remove this H, so this is the common thing. So what is the mechanism? Now I will write the mechanism, how it is formed. Actually what happened, HCN is a weak acid. It is very difficult to break it, right? But if we use a strong base, there is acid-base reaction. So we get salt plus water. And when this salt is formed, we get cyanide ion. And you know cyanide ion is now it becomes a good nucleophile. Okay, so in this way, this, you know, carbon has partial positive, oxygen has partial negative charge, and when this cyanide with complete negative charge, it attacks on cardinal carbon. Shift to the next. So we get O negative and Cn. So this is the product form, and then we have water. Okay. So this water, when attack on it, H plus ion from water attach here. So we get cyanohydrin and OH negative ion is removed. That means base is acting as a catalyst while forming cyanohydrin from HCN. Okay, when we use cyanohydrin, then OH negative, there is a role of OH negative only, because Na plus remains as such. OH negative ion get this H plus to form water, and we get cyanide ion. This cyanide, now it is a good nucleophile. Okay, so this good nucleophile can attack on carbonyl carbon, and we get at the end cyanohydrin. Okay, if we have acetaldehyde, we get acetaldehyde cyanohydrin. If we have formaldehyde, we get formaldehyde cyanohydrin. If we have acetone, we get acetone cyanohydrin. Right? Or if we have benzaldehyde, we get benzaldehyde cyanohydrin. So reaction is let us take now HCN in the presence of, better to use sodium hydroxide as well along with it, okay, because that will fasten the reaction. It is because to release cyanide ion, because it is a weak acid. HCN is a weak acid. That's it. This is acetaldehyde. So it is acetaldehyde cyanohydrin. This is benzaldehyde. So it is benzaldehyde cyanohydrin. This is acetone. So this is acetone cyanohydrin. Right? And why we use alkaline medium? Because HCN is a weak acid. It is very difficult to get more number of cyanide ions. So if we use alkaline medium, then cyanide ion is easily formed, and that is acting as a good nucleophile. Okay? Which one? The same? But it is a simple case. This is carbonyl group. Now HCN is a weak acid. As it is a weak acid, it is very difficult to get sufficient number of cyanide ions to carry out the reaction easily. So we use basic medium so that this acid base reaction takes place and we get cyanide along with water. And when as soon as this cyanide is formed, cyanide will easily attack on carbonyl carbon, because carbon being partial positive, so it is electrophilic, so nucleophile will easily attack here and we get O complete negative and carbon-carbon bond is formed, right? So then from the water, H plus ion will attack and OH negative is removed and we get cyanohydrin. That's it. Okay, Sai? Got it? So this cyanohydrin is a very useful synthetic reagent to prepare alpha hydroxy acids as well as alpha hydroxy amino acids. Okay? What I said? Cyanohydrin are useful synthetic reagents to prepare alpha hydroxy acids as well as alpha amino acids. Is it visible? Yes. Okay, so alpha hydroxy acids as well as alpha hydroxy amino acids. See, we have this is cyanohydrin. So if we hydrolyze it in acidic medium, then CN group is easily converted into COOH. So say carbon, saturated carbon next to COH, that is called alpha carbon, and this alpha carbon has OH group, so it is alpha hydroxy acids, carboxylic acids. Or if we treat this cyanide first with ammonia, so when ammonia, it is treated with ammonia, so we get OH is replaced by NH2 and water is removed, and on again hydrolysis we get, so say on alpha carbon there is NH2, so it is called alpha amino acids, alpha amino acids or alpha hydroxy acids that can be prepared from cyanohydrin. So it is a very useful synthetic reagent. Okay. Now, second, addition with sodium bisulfite, or we can say addition of sodium bisulfite or sodium hydrogen sulfite. Addition of sodium bisulfite or sodium hydrogen sulfite. So see, this is carbonyl group. Addition of sodium bisulfite or sodium hydrogen sulfite. So what is the product formed? Tell me. Reaction is reversible. Keep in mind. I'll let you know why it is reversible. See, NaHCO3 SO3 plus CO. Obviously, it is like this. So first of all, we get OH, ONA, sorry, because Na positive and SO3 negative. So 3H, but as soon as it is formed, we get this product, because H plus is more stable, and SO3 negative, here negative charge is delocalized. In this case, negative charge is more delocalized than on oxygen. So negative charge is more stable on SO3 rather than O alone. So there is proton shift. So this is the product formed, and this is a crystalline compound. Useful method to identify aldehydes and methyl ketones, because this SO3 negative, see NaHCO3, that gives Na plus and HSO3 negative. Okay, so S OH and double bond O and O negative, it is like this, S double bond O, sorry, lone pair, double bond O, OH and O negative, it is like this. Okay, so this O negative, you can write it like this, So this O negative has delocalization. This O negative has delocalization. That's why negative charge is more stable on SO3 rather than Na plus, because SO3 is like this. Okay, so it is SO3 1 2 3 4 5 6 7. Wait. SO3 negative and Na plus. One bond is formed with other. This O gets attached to next carbon. Okay, that's why it is like this now. This is attached to carbon. Okay, so O negative, it is delocalized because of two oxygens, but in O negative there is no delocalization. That's why this proton transfer takes place, and this compound is crystalline compound. Okay, and because of bigger size of nucleophile, bigger size of nucleophile, it will not attack sterically hindered carbonyl group or sterically hindered carbonyl carbon. That's why aldehydes and only methyl ketones, aldehydes and methyl ketones will react. For most of the ketones, reaction is backward. Okay, that's why NHCO3 is used for the even purification of the aldehydes and ketones. Only methyl ketones. For most of the aldehydes, reaction is forward, and for most of the ketones, it is backward. Yes. Sahil, are you writing something? Okay, so we should have high concentration of NHCO3, so that reaction is more in the forward direction. So we use saturated solution. Okay, and the compound formed is white crystalline solid, because sodium salts are white. Most of the sodium salts are white. Okay, so in this reaction, HSO3 negative is a weak nucleophile because of hindrance. This reaction can also be used first to identify and for the purification of aldehydes and ketones. For the purification it is also used, because once this complex is formed, if we treat it with HCl or NaOH in acid or base, we get back the same aldehyde or ketone. So in this way we get the same product. Yes, tell me. Along with sodium sulfide and water. In this case we get NaCl, SO2 and H2. Okay, so aldehydes and ketones can be regenerated by treating them with acid or base. So tell me, if we have a compound like this. First tell me what is the name of this compound. What is the name of this compound? What is the name of this compound? Write the name. Anybody, what is the name? It is like this. Yeah, please tell me the name. Don't tell you don't know. Very good, Harsh. It is benzophenone. Okay. So, write for sodium bisulfite, benzophenone fails to react with NaHSO3 because, is it visible? Yes. Because of two bulky phenyl groups which hinder the attack of SO3H negative nucleophile. So this is the first point to be noted about sodium bisulfite reaction. Second, sodium bisulfite addition compound, the formation of white crystalline compound is a test for carbonyl compounds. And third point which is to be noted, that it can be used to purify carbonyl compounds and to separate from non-carbonyl compounds. Because what we do, first we add NHSO3, sodium bisulfite. So sodium bisulfite will precipitate out carbonyl compounds as a bisulfite addition compound. When this bisulfite addition compound is formed, we will precipitate it out, we will filter it. So in the residue, we get that white crystalline compound, and then now it is separated from the non-carbonyl compounds because sodium bisulfite will react only with carbonyl compounds, right? So in this way, we have separated it. After the separation, we will add either acid or base in the bisulfite addition compound. which is in the form of residue, and then we will regenerate the carbonyl compound. In this way, we have to separate it from non-carbonyl compounds, or we can purify it. If impurities, others are in the form of impurities, so it can be used to purify and separate from other compounds. Any doubt in this part? It is very important. Actually, it is a sodium bisulfite is a test for carbonyl compounds, because when sodium bisulfite is added and white crystalline compound is formed, that means it is a carbonyl compound. Yes, anybody? Okay. Vasant, Ashish and Sahil. Sometime Harsh. They are active members. Where is Rishi? Varun, Yash, Charitra, Kashmira. Okay, good. Now, addition of Grignard reagent. Next one. For addition of Grignard reagent, that is Grignard reagent is RMJ X, right? So in this we have C double bond O. C double bond O when react with RMGX, we get, obviously you know, R is negative, MgX positive. It is like this. C is positive, O is negative. So R negative will surely attack on carbon, and it is O negative, MgX positive, and R. Right? And then on hydrolysis, we get OH and R along with MgXOH. Right? So this reaction we have covered in alcohol as well, that if we have formaldehyde along with, let us take methyl magnesium bromide, then acetaldehyde with methyl magnesium bromide and acetone with methyl magnesium bromide. So tell me, what are the products formed? What are the products formed? Yes, in first case, obviously it is like OMgBr, CH3, and on acid catalyzed hydrolysis, we get OH, CH3 along with MgBrOH, right? Okay, so this is CH3, CH2, OH. ethanol means primary alcohol. Formaldehyde will give primary alcohol. Formaldehyde will give primary alcohol. These are other aldehydes. Acetaldehyde or any other aldehyde, any other than formaldehyde. So first of all, same OMGBr, CH3, CH3H. See, CH3H as such, O is attached to MgBr, C is attached to CH3. Okay, and then on hydrolysis, see CH3H as such, see O becomes OH because say it is O negative, MgBr positive. So O negative is attached to H plus and MgBr with OH. CH3 along with Mj, Br and OH. Right? So this is actually CH3, CH, CH3, OH. That is propane 2-ol, or we can say secondary alcohol. So other aldehydes will give secondary alcohol. Right? Now tell me about this. Third one. In third case, these are CH3, CH3. Yes, it is visible. Yes. OMG, Br and CH3, right? And on hydrolysis, see CH3, CH3, CH3 remains as such. It becomes OH along with MgBrOH. Right? So what would we get? CH3, OH, CH3, CH3. And this is tertiary butyl alcohol. This is isopropyl alcohol, right? This is tertiary butyl alcohol, or we can say it is tertiary alcohol. So keep in mind, with Grignard reagent, formaldehyde upon hydrolysis, formaldehyde when react with Grignard reagent and on subsequent hydrolysis, we get primary alcohol. For other aldehydes, we get secondary alcohol. For ketones, with ketones, we will get tertiary alcohol. So that's all for the day. Thank you so much. Bye bye to all. Can I write here that with, see, formaldehyde, other aldehydes and ketones with Grignard reagent followed by hydrolysis. Okay, we get primary alcohol. Other aldehydes on the same line give secondary alcohol, and tertiary alcohol with same reagents we get tertiary alcohol. That's it. Okay. Done? Okay, bye, good night. Thank you. Very good, Aryan. Okay, bye-bye. Ashish. Okay, bye Kashmira. Good. You are active today. Bye Harsh.